You know that doing almost anything in a Swift app involves calling functions. Displaying an alert, you call a function. Fetching data from the network, you call a function. Sorting elements in a collection, you call a function. And even launching the app itself requires calling a function, even if you don't do it explicitly. But have you ever wondered what it actually means calling a function? What happens when the runtime encounters a function call? Does the compiler have anything to do with it? And can you influence their behavior to speed up your code? That's what we'll be discovering today. I'm Yakov, and in today's video, I'll talk about method dispatch in Swift. I'll explain its different flavors, their performance implications, and usage limitations. By the end of this episode, you'll know exactly why static functions are named so, and what price you pay every time you use the objc attribute. Subscribe to the Codebird for even more engineering content. And with that said, let's get started. The first thing we should consider is what method dispatch even is, because this is something your app uses thousands, if not millions of times each session. You know that most Swift objects can declare instance methods. Those methods are a classic tool of the object-oriented paradigm. There are objects, and each object can include some data and logic to operate on that data. We come to think of instance methods as parts of the instance itself. But in reality, the actual function bodies aren't stored with the instances they belong to. You can easily see why. These two methods are nearly identical, so duplicating their instructions in each and every object instance would only waste memory and bloat your executable. Instead, method implementations are stripped away and stored separately. Their signatures slightly changed to enable reusability. Each instance method gets this invisible self parameter, so you can access other symbols declared on the instance. When you call a method, the runtime needs to find its implementation in memory, call its address, and pass it all the arguments, including self. In other words, the method call needs to be dispatched to the implementation. And that's what method dispatch really is. It's a mechanism to discover, retrieve, and execute the implementation of a given method. Swift has multiple ways of doing so, and in many cases, it lets you choose the most appropriate one. Let's see our options. The most straightforward way to establish a connection between the method's signature and its implementation is to link them directly. As the compiler builds your code, it just inserts the actual memory addresses that correspond to each method's implementation. And this simple principle is the foundation of static or direct dispatch in Swift. It offers the best performance and highest degree of optimization. That's because the runtime doesn't need to do anything except execute the code at the given address in memory. When you want to declare a method on the type itself and not an instance of it, you mark the function with the static keyword. And static here refers precisely to static dispatch. Type methods always rely on it. Even though statically dispatched function calls are really fast, they still incur some overhead. It's fairly minimal, but if you want something even better than that, then you can inline the whole method implementation. This will effectively replace the function call with its actual body. Keep in mind though that excessive inlining results in inflated executables, because you literally prevent code reuse in this scenario. Swift offers two attributes for controlling the inlining behavior: inlineable and inline. The first one makes the function body visible across module boundaries, even though it doesn't force the actual inlining. The second attribute is more imperative. While it still doesn't force the compiler to do anything, it acts as a strong suggestion to either always inline the implementation or never do it. Unless you're working on something performance critical, I would recommend you to not mess with inlining. That's because even the advisory inlineable attribute can still have unintended consequences. For example, it can break your module's binary interface or ABI. In short, just leave these optimizations to the compiler. Static dispatch is the only flavor available in value types like structures. In reference types such as classes, you can enable static dispatch by using the final keyword. You can apply it to the class as a whole or its individual methods. And in many situations, the compiler adds this keyword behind the scenes, just as part of its optimizations. But maybe you know that marking a class as final has one more consequence. You won't be able to inherit from it or override its symbols in a subclass. In other words, this keyword will disable the inheritance mechanism and the polymorphism it provides. Why? Because inheritance-based polymorphism requires a more advanced form of method dispatch. Dynamic dispatch is more powerful because it can choose the right implementation among multiple candidates. The most common scenario when you need this is when your class is part of a larger class tree. At each level in this hierarchy, the class can either reuse its parent's implementation or override it with a different one. You can imagine tables printed on transparent film and stacked one on top of another. If the cell in the topmost table is filled, its value is used. If not, you just fall through the opening until you find a value on a deeper level. By the end of this process, the table should have no empty cells. How can you achieve this result with classes? One option is to simply traverse the entire hierarchy, find the first method implementation you encounter, and copy it straight to the resulting class. And that's precisely what final does. But you can't build a hierarchy if every class is marked with final. You need a different approach, and dynamic dispatch is the answer. It relies on a special in-memory mechanism. This mechanism dynamically resolves method implementations at runtime. Its name is vtable, or virtual table. The vtable looks very similar to what I described earlier. When a subclass is created, it inherits all entries from its parent's vtable. It's like having all cells empty. But the subclass can also replace individual pointers with overridden implementations. When you then build and launch the app, the runtime retrieves the vtable for each class and resolves the address of method implementations. The vtable is stored in each class's type metadata, and it can be accessed through the ISA pointer. You might have seen this property if you inspected a class instance with a debugger. So, as you can see, even though the runtime doesn't need to traverse the entire class hierarchy, it still needs to make two detours before it can call the implementation. First, it retrieves the type's vtable, and then it looks up the implementation address. Only after that can it execute the method's body. The runtime may need to perform hundreds, if not thousands, of vtable lookups every second. But it is highly optimized for that, and modern hardware is quite powerful. That is to say, you don't need to worry about having too much dynamic dispatch in most situations. In the end, this conceptual mechanism is nothing new. It's existed since the earliest object-oriented languages of the 60s, and the specific virtual table implementation is the product of the 80s and C++. Speaking of products of the 80s that influenced Swift, there is one more of them, and you use it every time you run code on Apple devices. I'm talking about Objective-C, of course. And Objective-C in turn was influenced by Smalltalk, especially when it comes to method dispatch. You see, in Objective-C, you don't call a method on the object. Instead, you send a message to the runtime. You ask it to locate the method's implementation and invoke it with the object as the self parameter. Each method is described with a selector, which is just a plain string. You can literally create a selector with a plain string and then perform it on an object. As you can imagine, this approach offers nearly endless flexibility, to the point where you can call arbitrary native methods right from your backend. Do I need to tell you should never do this? It goes without saying, right? Well, back to the point. Since Swift is designed for easy interop with Objective-C, it does offer a compatible mode. It is called Message Dispatch. You can enable it by adding the dynamic keyword to the symbol. Yeah, I know, you use dynamic to enforce message dispatch. The naming is just mind-blowing. And while you can do this with pretty much any symbol, there are very few reasons you should. Mostly they come down to situations where you need method swizzling or classic KVO. But one keyword you do use quite often is the Object-C attribute. What it does is exposes the symbol to Objective-C code and adds support for message dispatch. But it doesn't require it. So for example, if the method is later called from Swift, the runtime will upgrade it to use dynamic dispatch instead. And actually, Swift will try to upgrade method calls to the best of its ability. Consider this illustration. NSObject comes from Objective-C, and because of that, it uses message dispatch by default. So does NSViewController, which is an NSObject subclass. When the AppKit framework displays the viewController, it calls the viewDidLoad method, and this method calls its superclass's implementation. These two actions interact with the Objective-C runtime directly, and because of that, both use dynamic dispatch. But then, viewDidLoad calls fetchData, which is a pure Swift method that is neither final nor dynamic. That means it can use dynamic dispatch through a vtable. And finally, fetchData gets a URL from the getURL method. This one is marked with final, and this keyword makes it use static dispatch. So that's all the three method dispatch methods in just a handful lines of code. And all that brings us to the key question. Should you even care about method dispatch? Should I even care about making this video? Objective-C's message passing has worked decades ago on much less powerful hardware. If it is enough for nearly everything, why reinvent the wheel? I would argue it's not just about performance, but also clarity in software design and predictability in behavior. The single biggest benefit of dynamic dispatch is that it enables polymorphism, which is a prerequisite for extensibility. Without it, you lose the ability to design complex structures while avoiding code duplication. You can't extend an existing object, and you can't substitute it with an instance of its subclass. That holds true even if you don't care about these apparent violations of OCP and LSP, and you don't like inheritance, and you prefer composition with protocols instead. That holds true regardless. Because guess what? Protocols depend on dynamic dispatch just as well. Static dispatch, on the other hand, guarantees extreme predictability. When your object uses static dispatch, through a final keyword or otherwise, you don't risk calling the wrong method because of a typo or something else. In summary, method dispatch in Swift is yet another area where you're given a number of really powerful tools, each serving its own purpose. Your role as a software engineer is to analyze the task and choose the right tool for the job. And my role, in the scope of this channel, is to give you enough information so you can make the choice with confidence. I hope this video has been helpful for that. You can tell me what you think in the comments or by giving this video a like or dislike. If you want to see more engineering content, subscribe to the Codebird. I'll see you in the next episode. Until then, make your methods fly.